Hello, I'm Ken Mitchell, and welcome to Microsoft GameStack Live. I'm excited to share with you the following slides on AMD Ryzen processor software optimization. Thanks to the talented Andrew Ferrier from the Microsoft Xbox Advanced Technology Group for the invitation and his feedback. Let's begin. Today's agenda includes abstract, speaker biography, Zen 2 architecture processors, Zen 3 architecture processors, and best practices. Abstract. Join AMD on an adventure through Zen 2 and Zen 3 processors, which power today's game consoles and PCs. Dive into instruction sets, cache hierarchies, resource sharing, and simultaneous multi-threading. Journey across the sands of silicon to master microarchitecture and uncover best practices. I'm a principal member of technical staff in the AMD game engineering team, focusing on helping game developers utilize AMD processors efficiently. Recently, I worked on Doom Eternal and Godfall. Zen 2 architecture processors. Zen 2-based products exist in a wide variety of form factors. AMD Ryzen 4000 series mobile processors, codenamed Renoir, offer up to 8 powerful cores in ultra-thin laptops, typically at only 15 watts. These laptops are great for those with limited carry capacity. Next, AMD Ryzen 3000 series mainstream desktop processors, codenamed Matisse, offer up to 16 cores at up to 105 watts for gaming and beyond. Finally, AMD Ryzen 3000 series high-end desktop processors, codenamed Castle Peak, offer up to 64 cores at 280 watts. These products arm digital content creators and software developers to battle bake, combat compile, and rip render times. The custom-designed processors in the Xbox Series X and Xbox Series S leverage Zen 2 CPU and RDNA 2 graphics architectures. Zen 2 provides a significant advancement in CPU performance, delivering more than 4 times the performance of an Xbox One X. Note, Renoir has a similar CPU architecture, core count, and cache size, but a very different memory and graphics design. Speaking of microarchitecture, what is simultaneous multithreading? High-performance cores have gaps in utilization, which may be filled by additional hardware threads. This is simultaneous multithreading. Although each hardware thread has its own program counter and architectural register set, they share core resources. Consequently, there may be architecture-specific bandwidth and latency trade-offs. Skilled developers may apply knowledge of these trade-offs while optimizing for performance. Zen 2 supports two-way SMT and may run in either single-thread or dual-thread mode. Program thread select occurs during branch prediction and is typically done using round-robin scheduling. Some resources within the core may be shared while in dual-thread mode. The core is in dual-thread mode while both its logical processors are executing program threads. If either of the core's logical processors execute the operating system's idle thread, the core may return to single-thread mode. Disabling SMT and BIOS menu options will reduce the number of logical processors in the system and limit cores to operate only in single-thread mode. Let us review resource sharing definitions. Competitively shared. Resource entries are assigned on demand. A thread may use all resource entries. Watermarked. Resource entries are assigned on demand. When in two-threaded mode, a thread may not use more resource entries than are specified by a watermark threshold. Statically partitioned. Resource entries are partitioned when entering two-threaded mode. A thread may not use more resource entries than are available in its partition. Resource entries are unpartitioned while exiting two-threaded mode. Most resources are competitively shared. However, the floating point scheduler and memory request buffers, including the write combining buffers, are watermarked. Additionally, the op queue, store queue, and retire queue are statically partitioned. Typically, lightly threaded applications run best while cores are in single-thread mode in order to reduce resource sharing. The instruction set is the same regardless of single-thread or dual-thread mode. Zen 2 added cache line writeback and writeback no invalidate instructions. Vectorized instructions use the floating point schedulers and execution units. AMD and Intel processor results may not be binary equivalent for reciprocal and reciprocal square root instructions, although both vendors are ISA compliant. However, we intend AMD Jaguar and Zen to be equivalent for floating point instructions. Please note, Zen 2 does not support AVX 512 or AMX instructions. Software prefetch instructions, by definition, load a cache line from the specified memory address into the data cache level specified by the locality reference hint T0, T1, T2, or NTA. This instruction is implementation dependent. Prefetch, fill, and evict policies may differ for other processors. Policies for Zen 1, Zen 2, and Zen 3 are shown. Prefetch levels T0, T1, and T2 are implemented in hardware identically, all fill into the L1 cache. However, prefetch level NTA lines are marked for quicker eviction from the L2, and when eventually evicted from the L2 are not inserted into the L3. If a memory fault is detected, the instruction is treated as a no-op. Use software prefetch instructions on linked data structures experiencing cache misses. Use NTA on use one's data. While in dual thread mode, beware too many software prefetches may evict the working set of the other thread from their shared caches. Prefetching a few megabytes of data using the T2 hint may benefit one thread, but likely harm the other. Additionally, you may remove ineffective software prefetches found by PMC 52 hex. Cache details, including ways, associativity, inclusion policy, and write policy, are described in AMD software optimization guides. A high-level data flow view of the system may help illustrate possible bottlenecks. This slide shows an abstract diagram of an AMD Ryzen 4000 series mobile processor, codenamed Renoir. Imagine data moving from the DRAM on the far right through the data fabric, caches, and cores on the left. Each unified memory controller manages 64 bits of DRAM, for example, one 64-bit DDR4, or for example, two 32-bit LPDDR4. Note this is a single monolithic die SoC design where the orange-colored core complex L3 cache connects to the blue-colored data fabric at 32 bytes per cycle read and 32 bytes per cycle write. Unlike most AMD Zen 2 desktop products, this product has only 4 megabytes of L3 cache. The AMD Ryzen 7 4700G processor used later in many of our examples is based on Renoir. Next, this slide shows an abstract diagram of an AMD Ryzen 3000 series mainstream desktop processor, codenamed Matisse. This is a chiplet design with two core complex die, aka CCD. Each CCD has two 16 megabyte L3 caches. However, the L3 cache complexes within a CCD share a single link to the data fabric at 32 bytes per cycle read and 16 bytes per cycle write. Finally, this slide shows an abstract diagram of an AMD Ryzen 3000 series high-end desktop processor, codenamed Castle Peak. This topology with up to 8 CCDs is so large that I've shown it in quadrants for simplicity. Note, each quadrant looks similar to Matisse. However, Castle Peak has a much larger I/O die with additional unified memory controllers and PCIe lanes. You can add many GPUs and NVMe drives to this beast. As program threads are added to the system, both bandwidth and latency may increase. Each logical processor may have memory demand, software prefetch, and hardware prefetch requests. These requests to shared resources may cause cache evictions and misses. These misses may increase data fabric usage and add queuing delays. DRAM page conflicts may become more common. False sharing may become more harmful, and software prefetch instructions may become more beneficial. S&T dual thread mode may further increase both bandwidth and latency. Zen 3 architecture exceeded my expectations. Advances in Zen 3 microarchitecture included a whopping 19% desktop IPC improvement, a unified 8-core cluster for faster cache-to-cache transfers, double the L3 cache size, improved load store unit, wider issue and float and integer engines, improved SMT fairness, and new cryptography instructions. The bold text lines show resource sharing changes from Zen 2 to Zen 3. The integer scheduler, integer register file, and load queue have changed from competitively shared to watermarked. These changes improved SMT fairness. Otherwise, resource sharing looks like Zen 2. There have been some changes to the instruction set. Zen 3 added vectorize AES and vectorize carry list multiply instructions often used in cryptography. Additionally, parallel bits extract and parallel bits deposit instruction latencies have been reduced to only 3 cycles. Please note, Zen 3 does not support AVX512 or AMX instructions. Here we have an abstract diagram of an AMD Ryzen 5000 series mainstream desktop processor, codenamed Vermeer. This is a chiplet design where each core complex die has a unified 8-core cluster with a massive 32 megabyte L3 cache. This change greatly improved cache hit rate and reduced data fabric contention for some applications. Zen 3 documentation added hardware prefetcher descriptions. Yay! For workloads that miss in the L1 or L2 caches, software may get improved performance if data structures are designed such that the data access patterns match one of these listed behaviors. The stream and stride prefetchers are most noteworthy in my opinion. Stream prefetchers may fetch additional sequential cache lines in ascending or descending order. Stride prefetchers may fetch additional cache lines when each access is a constant distance from the previous. Best practices. Some best practices include audit content, use modern sync APIs, avoid false sharing, prefer data access patterns matching hardware prefetchers, use software prefetch instructions for linked data structures experiencing cache misses, and test application scalability from 1 to the number of logical processors. Audit content. Ask artists to recommend scenes of interest for profiling. For example, an indoor dungeon with heavy occlusion, an outdoor city, an outdoor forest with alpha transparency, large crowds, or a specific time of day. UE4 developers may find some performance issues simply by running map check, especially for issues related to actor shadows. Unity developers may enforce minimum standards using the asset post processor. Check stats before CPU profiling. If the scene far exceeds its draw budget or has many duplicate objects, especially physics objects, consider reporting the issue to its artist and profiling a different scene. Otherwise, you may risk profiling hot spots which may not be hot after the art issues are resolved. Use modern sync APIs. Some modern sync APIs leverage AMD's mwaitx instruction efficiently to wait on address or timeout. Legacy sync APIs may have unneeded syscall overhead. User spin locks may consume OS thread scheduling resources unnecessarily since the OS scheduler may be unable to determine if it should yield to another program thread rather than spin. This chart shows over a 10% performance improvement by using standard mutex on modern sync API. Here's the source code for the main function used in the exclusive lock microbenchmark. Basically, it times how long all threads took to execute the callback function. The code for the bad spin lock and its callback function are shown on this slide. A bad user spin lock may waste power and drain your laptop battery. Worse yet, the OS scheduler may be unable to determine if it should yield to another program thread with payload work rather than spin. Note, the while loop does not include a pause instruction. Ouch. This spin loop may consume core resources in an overly aggressive manner while doing non-payload work, and be very painful for older processors with less SMT fairness. WaitForSingleObject with create mutex are shown in this example. These two APIs have been around for a long time. The WaitForSingleObject function checks the current state of the specified object. If the object's state is in non-signaled, then the calling thread enters the wait state until the object is signaled or the timeout interval elapses. Thus, WaitForSingleObject may not suffer from the OS thread scheduling and core resource sharing issues caused by some bad user spin locks. Note, this example requires some initialization in main. Better yet, standard mutex is even faster than WaitForSingleObject. This modern sync API is based on a slim reader-writer lock and Microsoft's implementation, which can be verified using the Windows Performance Analyzer. In my testing, standard shared mutex and intercritical section also outperformed WaitForSingleObject. Finding and fixing false sharing issues may have great performance benefits. This micro benchmark showed greater than 500% improvement. For this example, we create an array of thread handles as well as an array of thread data of the same length. Before the optimization, the thread data array was compact, but unfortunately the different threads were likely to modify the same cache line while using their thread data in the callback function. Simply padding each thread data element using align as of the native cache line size resolved this issue. Although align malloc is preferred, the new operator was used in this example simply due to slide space constraints. Preferred data access patterns matching hardware prefetcher behaviors, especially for streaming and stride. The streaming hardware prefetcher uses a history of memory access patterns to fetch additional sequential lines in ascending or descending order. This simple example may trigger a streaming hardware prefetcher as it iterates the contiguous array. Similarly, iterating standard vector may also trigger this prefetcher. The stride hardware prefetcher uses a memory access history of individual instructions to fetch additional lines when each access is a constant distance from the previous. 2 strides are detected in the code sample shown. Again, iterating standard vector may also trigger this prefetcher. However, the stream and stride code snippets may not trigger a hardware prefetcher if they had iterated instead using a linked list data structure with nodes scattered randomly across memory. Use software prefetch instructions for linked data experiencing cache misses. In this example, performance improved over 60% using software prefetch optimizations. Results may vary significantly for systems with different cache sizes or different memory latency. The NVIDIA physics calculate demo iterates a standard vector of pointers. Consequently, the stream and stride hardware prefetchers are of little help due to the pointer chase. Before the optimization, many of the data accesses in the innermost loop missed the 4 MB last level cache of the AMD Ryzen 7 4700G. Since the convex class member data is not public, offset of keywords cannot be used, and thus literal offsets are shown. Although not illustrated in this example, additional performance may be possible by reordering the hot member data to occupy only 1 cache line rather than 4. Some applications scale very well with many logical processors. Cinebench R23 improved 28% thanks to SMT on this system configuration with 8 cores and 16 logical processors. The gthread count command line option is a very close approximation to the actual number of logical processors used for this application. A game's thread scaling depends heavily on the game engine, scene, and settings. It also depends on the system's GPU, CPU, memory, etc. We often see game performance level off as we become bound by the GPU. Testing at lower resolutions may help forecast performance of future faster GPUs. In UE 4.26, the core limit command line option will influence the number of worker threads to spawn for the task graph. Additional threads may also be created. For the Infiltrator demo, the Windows Performance Analyzer revealed the hottest threads were render thread 1, RHI thread, and main, followed by the task graph threads. In our scalability tests, the average performance peaked at core limit equals 4 and remained relatively flat at higher core limit values. Percentiles of frame times may reveal performance issues unnoticed by averages. Be sure you have sufficient samples, especially for 3 sigma and higher, when making comparisons. See the Wikipedia 68-95-99-7 rule. In this example, we see performance is lost at high core limit values. The default value is effectively the number of logical processors minus 2. Compare the frame times of the effective default core limit equals 14% difference from the optimal core limit equals 4. The mean is 3% slower. The 68th percentile is 5% slower. The 95th percentile is 5% slower. And the 99.7 percentile is 3% slower. When run as administrator with advanced settings, AMD Microprof can be used to show the actual thread concurrency histogram for a process. On the left, SMT threads were used 13% of the time while using the default core limit value. On the right, SMT threads were used only 2% of the time while using the core limit equals 4 for slightly higher performance. Searching the internet for recent technical press gaming reviews of SMT on versus SMT off using BIOS settings may show mixed results which demonstrate the need for testing application scalability during game development. In our experience, some games improved by 5% or more after reducing the number of worker threads. Be sure to profile your application, especially for your minimum, recommended, and ultra PC specs, to determine the ideal number of worker threads. This advice is specific to AMD processors and is not general guidance for all processor vendors. Generally, applications show SMT benefits and use of all logical processors is recommended. However, games often suffer from SMT contention on the main or render threads during gameplay. One strategy to reduce this contention is to create threads based on physical core count rather than logical processor count. Profile your application or game to determine the ideal thread count. Game initialization, including decompressing assets and compiling and warming shaders, may benefit from logical processors using SMT dual thread mode. However, gameplay may prefer physical core count using only SMT single thread mode. I recommend adding game options to set max thread pool size, force thread pool size, force SMT, and force a single NUMA node, which will implicitly force a single processor group. And finally, avoid setting the thread pool size as a constant. A core count detection code sample is available at gpuopen.com. We intend to update it to add a low cores threshold and clarify our guidance regarding recommendations for gameplay and game initialization. Pseudocode is shown. Again, this is general guidance only for AMD processors and is based on our experience. It is subject to change. Profile your application for best performance. Below are some tips for applications which lose performance at high thread counts. Reduce logging verbosity. Logging is often serial execution and may cause cache pollution. Minimize logging within parallel worker threads. One log event is faster than n log events. Consider disabling logging by default. Tune the minimum batch size. The batch is the partition of parallel work executed by a thread. Try minimizing page contention by setting the minimum batch size such that its data is at least one page. Pages are typically 4 kilobytes. Reduce the worker thread count. More ready threads than logical processors may result in unnecessary context switching. Less threads may indirectly increase the batch size. Less threads may also result in less resource sharing, especially of SMT cores and caches. This may improve the cache hit rate of a time-critical, latency-sensitive thread. Although not shown in our example, moving hot threads which do not share data to cores connected to different last-level caches may be beneficial and worth experimentation. Do you want to know more? Developer.amd.com has software optimization guides for Zen 2 and Zen 3. Discover your best graphics performance by using our open source effects, SDKs, tools, and tutorials at gpuopen.com. Design faster, render faster, iterate faster. Your time is valuable, and I appreciate that you have chosen to spend it with me. I can't wait to see what you create.